Half of the universe's normal matter has vanished. This is not a story about dark energy or dark matter, but a mystery of the very atoms that build everything we see. Scientists have a cosmic receipt from the Big Bang itself, a precise tally of all the ordinary matter that should exist today, yet our telescopes can only find about half of it. Trillions of suns worth of material, the protons and neutrons of you and me and every star, are simply unaccounted for. By the end of this journey, you will understand the ingenious hunt for this missing half and where it might be hiding in the shadows of space. We will follow clues from the first light of creation to the faint glow of million-degree filaments, asking how an entire universe of material could simply disappear. What does it mean for our place in the cosmos if we cannot even find the stuff we are made of? Think of it as the universe's original recipe, a list of ingredients written in the very first light. That light is the cosmic microwave background, the faint, cold whisper of radiation that fills all of space, a relic from when the universe was a mere 380,000 years old. It is our most pristine snapshot of the infant cosmos, and etched into its subtle temperature variations is a precise cosmic budget. This budget tells physicists exactly how much ordinary matter, the protons and neutrons that form atoms, should have been created in the Big Bang. This type of matter has a scientific name, baryonic matter, named for the heavy particles that make it up. According to that ancient blueprint, about 5% of the total mass and energy of the universe today should be this baryonic stuff, the building blocks of stars, planets, and us. It is a number derived from fundamental physics, and it is exquisitely precise, so we have the theoretical ledger, a clear expectation from the dawn of time. The next step seems straightforward. Take a cosmic inventory. Point our most powerful telescopes at the sky and count everything we can see. Catalog every brilliant galaxy, from majestic spirals to fuzzy ellipticals. Tally every star within them and every wisp of glowing gas cloud drifting in the voids between. Add it all up, and the total should match that 5% figure from the cosmic microwave background. But it does not even close. When astronomers complete this grand tally of the visible universe, they arrive at a shocking and persistent shortfall. Only about half of the expected baryonic matter is accounted for. The other half, a staggering amount of material equivalent to trillions of our suns, is simply missing from the observable ledger. This is not a small accounting error or a case of misplaced decimal points. We are talking about half of all the normal matter in the entire cosmos. To put that scale into a more human perspective, imagine meticulously planning a construction project. You order every single brick, beam, and pane of glass needed to build a vast city. The delivery manifests confirm every item has been shipped, but when you arrive at the construction site, only half of those materials are there. The other half of your bricks and beams have vanished without a trace. The universe has provided us with a manifest, a receipt from the Big Bang itself, confirming the creation of all this baryonic matter. Yet our observational tools, our eyes on the cosmos, can only find about 50% of it. This presents a profound and unsettling puzzle. If our understanding of the Big Bang is correct, and all evidence suggests it is, then the matter is not gone. It must be somewhere. It is hiding in plain sight, in a form or a place we have not yet learned to see. The search for this missing half has become one of the greatest detective stories in modern astrophysics, a hunt that forces us to question not what the universe is made of, but how it is put together. To understand the scale of this cosmic shortfall, we must first trust the receipt. The evidence for all that missing material comes from a time before stars, before galaxies, before atoms were even fully formed. In the universe's first 3 minutes, Conditions were so unimaginably hot and dense that nuclear fusion occurred everywhere at once, a brief and furious firestorm known as Big Bang nucleosynthesis. During this flash of creation, the primordial soup of particles cooked up the lightest elements in a very specific recipe. Hydrogen was the overwhelming majority, but alongside it came precise, trace amounts of helium and a form of hydrogen called deuterium, which has an extra neutron in its nucleus. The key is deuterium. Think of it as a cosmic canary in a coal mine, a sensitive witness to the conditions of that first moment. The amount of deuterium produced is exquisitely dependent on one thing: the density of baryons, the protons and neutrons that make up normal matter. If the early universe was packed with more baryons, nuclear reactions would have destroyed nearly all the deuterium. If it was less dense, more deuterium would have survived. So, by measuring how much deuterium exists today in the most ancient, pristine pockets of gas we can find, we can work backwards. We can calculate the exact density of baryonic matter that must have been present during those first 3 minutes. This gives us a number, a precise cosmic budget for all the normal matter the Big Bang ever produced. And this is not a rough estimate. The predictions from nuclear physics, tested in laboratories here on Earth, align perfectly with the deuterium we observe in clouds of gas so old they have never been touched by star formation. The agreement is stunning, a triumphant confirmation of our understanding of the universe's first moments. This primordial receipt tells us with high confidence exactly how much baryonic stuff the universe started with. It is our baseline, our ground truth. Every subsequent inventory of the modern universe, every count of stars and galaxies and gas, must ultimately reconcile with this number from the dawn of time. The crisis begins when we bring that ancient receipt to the modern cosmic supermarket and find that half the items on the list are not on the shelves. The discrepancy is not a flaw in the receipt, it is a clue. It tells us the universe has been hiding its assets, storing half of its normal matter in a form we have only just begun to see. The story of the missing matter gains a second, independent witness, one that paints a picture of the universe in its adolescence. 380,000 years after the Big Bang, the cosmos underwent a fundamental change. It had expanded and cooled from a searing plasma to a state where electrons could finally settle down and combine with atomic nuclei, forming the first neutral atoms. In that moment, a fog lifted. Light, which had been trapped, bouncing endlessly between particles, was suddenly set free. That first flash of liberated light has been traveling across an ever-expanding universe ever since, stretched by the fabric of space itself into a faint, cold microwave glow that permeates every corner of the sky. We call this the cosmic microwave background, and it is the oldest photograph we will ever have of our universe. Missions like the European Space Agency's Planck satellite have spent years mapping this ancient light in exquisite detail. To our eyes, these maps look like a field of static, but to cosmologists they are a treasure map. The subtle variations in temperature, the tiny hot and cold spots that differ by mere millionths of a degree, are not random noise. They are whispers from the infant cosmos, imprints of sound waves that were rippling through the primordial plasma. The size and distribution of these patterns are a cosmic fingerprint, and they encode critical information about the contents of the early universe, including the density of baryonic matter. It works like an echo in a cavern. The characteristics of the echo tell you about the size and shape of the cavern and what it is filled with. The patterns in the cosmic microwave background tell us, with astonishing precision, how much ordinary matter was present when the universe was only 380,000 years old. Crucially, this measurement is completely independent from the one we get from the primordial deuterium. It comes from a different physical process at a different moment in cosmic history, using a different type of observation. Yet when scientists calculate the baryon density from the cosmic microwave background, the number they get is in perfect agreement with the number from Big Bang nucleosynthesis. This is not a coincidence, it is a profound confirmation. Two separate lines of evidence, one from the universe's first 3 minutes and one from its first 380,000 years, are telling us the exact same story. The total budget of baryonic matter was set in stone long before the first star ever flickered into existence. This agreement solves one mystery while deepening another. It confirms beyond any reasonable doubt that our understanding of the universe's earliest chapters is correct. The matter was created, the receipt is valid. Therefore, the missing half of the universe's normal matter cannot have simply vanished or been destroyed. It must still be out there, woven into the fabric of the cosmos in some form that our current telescopes, designed to see blazing stars and glowing gas, are virtually blind to. The cosmic microwave background acts as a seal on the ancient ledger, proving the inventory was complete. Our task now is not to question the ledger, but to learn how to read the hidden entries, to develop new eyes that can see what the ancient light already knows is there. Armed with that ancient receipt, astronomers turn to the modern universe to conduct the most ambitious audit in history. They began a great cosmic census, a monumental effort to count and weigh every single piece of ordinary matter we can possibly see. This meant surveying the entire luminous universe star by star, galaxy by galaxy. With powerful telescopes, they tallied the mass locked within the brilliant cores of hundreds of billions of galaxies, each one a sprawling island of light. They measured the diffuse clouds of gas and dust swirling within those galaxies, the raw material for future generations of stars. They even peered into the vast spaces between galaxies, into the hearts of immense galaxy clusters, where they found enormous reservoirs of superheated plasma, gas so hot it glows in X-rays. The numbers from this census are almost beyond comprehension, involving trillions upon trillions of stars. Yet, when the final calculations were complete, a sobering truth emerged. The sum total of all this visible, glowing, detectable matter accounted for only about half of the baryons promised by the primordial receipt. Even after counting every sun and every nebula we can photograph, a gaping hole remains in our cosmic inventory. It is a definitive proof that the universe we see, in all its splendor, is merely the tip of a vast material iceberg. The shining stars and glowing gases are just the most obvious part of the story, the part that shouts for attention. The rest of the normal matter, the silent majority, must be hiding in the dark, cold spaces between the bright lights, waiting for us to learn how to see it. This vast, unseen ocean between galaxies is our first and most logical hiding place. Known as the intergalactic medium, it is the space between islands of light, a cosmic wilderness that is anything but empty. It is filled with a ghostly fog of gas, primarily hydrogen and helium, the original raw materials of creation. But this fog is so incredibly thin, so diffuse, that a single cubic meter of it might contain only a single atom. Compare that to the air we breathe, which has trillions upon trillions of molecules in that same space. This extreme tenuity is precisely why it has been so hard to see. It does not glow like a star or shine with the fierce heat of cluster gas. It is dark, cold, and nearly transparent. To find matter here, astronomers needed to become cosmic detectives, using not flashlights but the universe's own natural beacons. Their tool of choice is the quasar, the brilliant core of a distant galaxy powered by a voracious supermassive black hole. A quasar is so luminous it can outshine an entire galaxy, acting as a brilliant lighthouse shining from the far edge of the observable universe. As this piercing beam of light travels for billions of years on its journey to our telescopes, it passes through the countless filaments and clouds of the intergalactic medium. And here the gas leaves its fingerprint, atoms within the fog, particularly hydrogen, are very picky about the light they absorb. They only interact with very specific colors or wavelengths. When the quasar's light, which contains a full rainbow of colors, hits a cloud of hydrogen, the gas greedily sips away that specific wavelength. This theft leaves a dark line, an absence, in the otherwise complete spectrum of the quasar's light. But the universe is not filled with just one cloud. It is a complex, tangled web. As the light passes through countless clouds at different distances, each one absorbs its specific color. The result is a spectacular pattern called the Lyman-Alpha forest. When scientists spread the quasar's light into a spectrum, they do not see a clean rainbow. They see a forest of dark absorption lines, each one a shadow cast by a separate filament of hydrogen gas across cosmic time. By decoding this forest line by line, astronomers can map the invisible. They can chart the density, temperature, and distribution of the intergalactic medium in 3 dimensions. This technique has revealed that the spaces between galaxies are not barren voids, but are richly structured, filled with a delicate cosmic web of gas. And the tally from this method is enormous. A significant portion of the missing baryons do, in fact, reside in this warm-hot intergalactic medium. Yet, frustratingly, even this vast and intricate reservoir does not fully balance the books. While it accounts for a huge chunk of the missing material, the most precise measurements suggest there is still a portion of the universe's normal matter that remains unaccounted for, hiding in an even more elusive state. The intergalactic medium was a major discovery, but the hunt is not over. The final pieces of the puzzle must be hiding somewhere even darker, even more diffuse, challenging our very methods of perception. The hunt for the missing matter now leads us to a ghostly, superheated ocean, a state of matter so extreme it defies our everyday senses. This is the warm-hot intergalactic medium, or the WHIM, the current leading suspect in our cosmic detective story. Picture not a cloud of gas, but a thin, searing mist, heated to temperatures between hundreds of thousands and millions of degrees. At such incredible heat, the atoms are not merely atoms, they are violently torn apart. Electrons are stripped from their nuclei, creating a soup of charged particles known as a plasma. This plasma does not glow with the gentle light of a star. Instead, it whispers in a language we cannot see, emitting only the faintest flicker of high-energy X-rays. This is why it has remained hidden for so long. Our eyes and even our optical telescopes are blind to it. The WHIM is theorized to be woven into the very fabric of the cosmos, tracing the invisible scaffolding of the universe. This scaffolding is the cosmic web, a vast network of filaments made primarily of dark matter, upon which galaxies are strung like glittering beads. The missing baryons are thought to be concentrated along these dark threads, a superheated fog clinging to the universe's hidden skeleton. Finding it, however, is a monumental technical challenge. Its X-ray signal is not just faint, it is drowned out by the cacophony of brighter sources, like the X-ray glare from colossal galaxy clusters or distant, active black holes. It is like trying to hear a single violin playing softly in the middle of a roaring hurricane. To listen for that violin, astronomers have had to become extraordinarily clever. They use natural cosmic lighthouses just as before, but they look for a different kind of shadow. When the light from a distant quasar passes through the WHIM, it does not encounter cool hydrogen atoms. It passes through that soup of shattered atoms, where elements like oxygen have been stripped of most of their electrons. These highly ionized atoms can still absorb specific, very high-energy wavelengths of light. So, by carefully analyzing the X-ray spectrum of a quasar, scientists can search for the telltale dark lines, the fingerprints, left by this million-degree oxygen. Finding these absorption lines is like discovering the signature of the ghost. It confirms the WHIM is there, it maps its location, and it allows us to estimate just how much of this superheated material is woven through the voids. Recent observations from powerful X-ray observatories have done exactly that, providing some of the most compelling direct evidence that a significant portion of the missing baryons are indeed hiding in this elusive hot phase. The WHIM is no longer just a theory, it is a reality we are beginning to measure. Yet, even as we confirm its existence, a question lingers. Does this hot, filamentary fog contain all of the remaining missing matter, or is there still a final, even more elusive component waiting to be found? The search for the missing matter leads us not only into the deep voids, but right to our own galactic doorstep. Surrounding majestic spiral galaxies like our Milky Way, computer simulations predict the existence of a vast, hidden atmosphere, a million-degree cloak of gas known as a galactic corona or a hot halo. This is not the familiar disk of stars and dust we see in photographs. It is an immense, spherical shroud that can extend for hundreds of thousands of light years beyond the visible galaxy, a tenuous yet colossal reservoir of superheated plasma. If these halos are real and as massive as models suggest, they could hold a staggering amount of baryonic matter, potentially accounting for a significant portion of the missing material in our own cosmic neighborhood. Think of a galaxy not as a flat, shining disk, but as a brilliant jewel embedded within a giant, invisible sphere of searing mist. The jewel captures our attention, but the true bulk and scale of the object may lie in that vast, transparent sphere. For decades, this was purely theoretical, a prediction born from supercomputer models of galaxy formation and evolution. The challenge was one of perception. This hot gas does not emit the kind of light our eyes can see. Like the Warm-Hot Intergalactic Medium, it whispers in X-rays, and its signal is incredibly faint and diffuse, spread over an enormous area of sky. Detecting it is like trying to see the heat haze rising from a desert road at night, using only a telescope that is also pointed at a blazing bonfire. The glow from brighter X-ray sources in the foreground and background completely overwhelms the subtle signature. To find this ghostly halo, astronomers needed a new strategy, a way to listen for its whisper amidst the cosmic noise. They turned to a technique not unlike the one used with quasars, but on a much closer scale. Instead of a distant beacon, they used bright X-ray sources located behind our own galactic halo, such as active galaxies far beyond the Milky Way. As the X-rays from these distant sources travel through our galaxy's corona on their way to Earth, the hot gas in the halo should absorb specific wavelengths, leaving tiny, telltale dips in the spectrum. Finding these absorption lines is the key to proving the halo's existence and measuring its contents. This is where observatories like the European Space Agency's XMM-Newton have begun to change the game. In a series of meticulous observations, scientists have trained these powerful X-ray eyes on carefully chosen background targets, analyzing the light with extraordinary precision. And the results are tantalizing. They have detected the spectral fingerprints of highly ionized oxygen, the signature of gas heated to millions of degrees, exactly where the models predicted the Milky Way's corona should be. This is not just a hint, it is direct evidence that our galaxy is enveloped in a massive, hot atmosphere. Even more compelling, similar observations are now suggesting that other spiral galaxies possess these extended coronas as well. This transforms our understanding of a galaxy's anatomy. A substantial fraction of its normal mass, perhaps even as much as is contained in all its stars, may not reside in the glittering disk we admire, but in this immense, invisible, superheated cloak. It is a hidden reservoir of baryons, a solution to the missing matter mystery that has been hiding in plain sight, shrouding the very galaxies we call home. The discovery of these coronas brings us closer to balancing the cosmic books, suggesting that a great deal of the universe's ordinary matter is not lost in the distant voids. but is much closer, woven into the extended atmospheres of galaxies themselves. Yet the final accounting is not complete, and the hunt must push into even more elusive frontiers. The universe hides its secrets not in darkness, but in a form of light our eyes cannot perceive. The challenge of finding the missing baryons is a problem of physics and perception, dictated by two simple factors, temperature and density. The gas we are searching for exists in a state that is perfectly engineered to evade our traditional telescopes. Consider a cloud of gas at a relatively cool 10,000 degrees. It would glow, but not in the colors we see. It would emit ultraviolet light, a form of energy that is almost entirely blocked by our planet's protective atmosphere. From the surface of Earth, this signal is simply erased, an invisible whisper silenced before it can reach our instruments. To catch it, we must place our detectors above the atmosphere, on satellites orbiting in the silent vacuum of space. But the challenge only deepens with temperature. The most promising hiding places, the Warm-Hot Intergalactic Medium and galactic coronas, are not merely warm, they are infernos. At millions of degrees, matter behaves radically differently. Atoms are shattered into a plasma of nuclei and free electrons, and this searing soup emits light of an even higher energy, soft X-rays. Here, the problem is not just absorption, it is faintness. This hot gas is incredibly diffuse, spread over colossal volumes of space. It does not concentrate itself into bright, compact objects like stars or galaxies. Instead, it forms a pervasive, almost uniform fog, a ghostly haze with no sharp edges or clear boundaries. The X-ray signal from any single point in this fog is vanishingly weak, a candle flickering miles away on a foggy night. This combination of extreme temperature and extreme thinness creates the perfect cosmic blind spot. Our magnificent optical telescopes, built to capture the glorious light of stars, are utterly blind to it. They look right through this million-degree plasma as if it were not there at all. To find it, astronomers have been forced to become masters of indirect detection, turning the hunt into a delicate game of cosmic forensics. They rely on techniques like absorption spectroscopy, analyzing the light from distant beacons to find the subtle shadows cast by the invisible gas. They use statistical stacking, combining the faint signals from thousands of different lines of sight to build up a detectable whisper from a chorus of silence. Every piece of evidence is circumstantial, a clue painstakingly gathered to build a case against the void. It is a testament to human ingenuity that we can find anything at all in such an elusive medium, searching for the outline of a ghost by the way it dims a distant light. The first and most direct method in this cosmic investigation is absorption line spectroscopy, a technique that turns the universe itself into a vast forensic laboratory. To understand it, think of light not as a single color, but as a complete rainbow, a spectrum that contains a unique chemical fingerprint of its source. When astronomers point a telescope at an object like a distant quasar, they use a spectrograph to spread its light out into this full rainbow. If the path between that quasar and our telescope were perfectly empty, the spectrum would be smooth and continuous. But the cosmos is not empty. It is filled with an invisible fog of gas. As the quasar's light travels for billions of years, it passes through countless clouds and filaments of this material. And here is the crucial part: atoms are very selective. A hydrogen atom, for instance, will only absorb one very specific shade of red light. So when the quasar's light passes through a cloud of hydrogen, that specific shade is siphoned away, leaving a thin, dark line in the otherwise pristine rainbow. Each element creates its own distinct set of lines, a unique barcode imprinted on the light. By reading this barcode of shadows, astronomers can identify not only what the intervening gas is made of, but also how hot it is, how dense it is, and how far away it lies. For the hunt for the missing baryons, the target is not cool hydrogen, but the searing plasma of the warm-hot intergalactic medium. At millions of degrees, ordinary atoms are shattered. Oxygen, for example, is stripped of most of its electrons, becoming what scientists call highly ionized oxygen-7 or oxygen-8. These wrecked atoms still absorb light, but they do so at very specific, high-energy wavelengths in the ultraviolet and soft X-ray part of the spectrum. Finding the dark absorption lines from these ions is the definitive proof, the fingerprint left at the scene, confirming the presence of the million-degree gas. The challenge is that this fingerprint is incredibly faint, etched into light that has traveled across the universe. Detecting it requires not just any telescope, but the most sensitive instruments we have ever built, like the Hubble Space Telescope's spectrographs for ultraviolet light. Each successful observation is a triumph of precision, a single thread of evidence pulled from a cosmic haystack. With enough of these threads gathered from looking at hundreds of quasars, we can begin to weave a map of the invisible web, proving that the missing matter is not just a theoretical idea, but a physical reality waiting to be decoded. But a single fingerprint is not enough to map an entire ghost. The absorption method gives us proof the gas is there along specific lines of sight, but to truly see the shape of the hidden structure, we need a different tool. We need to try and photograph the ghost itself to capture its own faint glow. This leads to the second major investigative technique, hunting for the X-ray emission from the Warm-Hot Intergalactic Medium. The principle is straightforward. If this gas is heated to millions of degrees, it should emit a faint whisper of X-ray light. The problem is one of profound weakness. The signal from any single cosmic filament is so incredibly faint that it drowns completely in the background noise of the universe, like a single firefly trying to outshine a city's skyline. Our current X-ray telescopes, as powerful as they are, simply cannot pick out that solitary firefly. So, scientists had to devise a way to combine thousands of fireflies into a single, detectable beacon. They turned to a powerful statistical technique called stacking. Imagine you are in a vast, dark field on a cloudy night, trying to see the faint glow of a distant town. You cannot see it with your naked eye, but if you take 1,000 photographs, each one slightly misaligned, and then digitally combine them all, averaging out the random noise of the atmosphere, the steady, collective light of that distant town will slowly emerge from the darkness. This is precisely what astronomers do. They use sophisticated computer simulations of the universe, which predict where the densest filaments of the cosmic web should be located. They then take X-ray observations from telescopes like NASA Chandra X-ray Observatory and the European Space Agency's XMM Newton, and they focus not on one spot, but on thousands of predicted filament locations. They stack the data, aligning and averaging the X-ray signals from all these different patches of sky. The random noise, the static of the cosmos, averages toward zero. But if there is a real, consistent, ultra-faint X-ray glow coming from those predicted web-like structures, it will gradually build up, revealing itself in the combined data. This painstaking process has yielded some of the most tantalizing and direct evidence we have. In recent years, by stacking observations from vast regions of space, teams of researchers have reported detecting a faint, diffuse X-ray signal that aligns almost perfectly with the predicted architecture of the cosmic web. It is as if we have developed a new kind of vision, one that can finally perceive the universe's hidden skeleton not by the shadows it casts, but by its own ethereal million-degree glow. This evidence remains debated, as pushing instruments to their absolute limits always invites scrutiny, but the promise is extraordinary. Stacking offers a potential path to not just confirm the WHIM existence, but to eventually chart its full, intricate structure across the heavens, transforming our maps of the cosmos from a scattering of bright islands to a complete picture of the luminous web that connects them all. There is a third, more subtle way to see the invisible, one that listens for the echo of creation itself. This method relies on a phenomenon called the sunyaev-zeldovich effect, a clever cosmic trick that uses the oldest light in the universe as a backlight to reveal what lies in front of it. The principle is beautifully indirect. Picture the cosmic microwave background, that cold, ancient whisper from the Big Bang, as a uniform screen of light bathing the entire cosmos. Now imagine a vast cloud of incredibly hot gas, like the plasma in a galaxy cluster or a filament of the Warm-Hot Intergalactic Medium. As the delicate CMB photons travel through this searing cloud, they do not simply pass through untouched. They collide with the energetic electrons swirling in the hot plasma. In these collisions, the photons get a tiny boost of energy, a kick that shifts them to a slightly higher frequency. It is a minuscule effect, like a gentle nudge, but it leaves a mark. On our maps of the cosmic microwave background, the region of sky behind that hot gas cloud appears ever so slightly cooler at one frequency and warmer at another, a distinct fingerprint of distortion imprinted on the primordial light. The brilliance of this method is that it does not depend on the gas being bright enough to see on its own. It does not require the gas to emit any light whatsoever. Instead, it reveals the gas by the shadow it casts on the oldest canvas in the universe. By scanning the sky with exquisitely sensitive radio telescopes designed to measure the CMB's temperature in minute detail, astronomers can map these subtle distortions. Each distortion is a signpost pointing directly to a reservoir of hot, diffuse plasma, regardless of how faint or spread out it is. This makes the sunyaev-zeldovich effect a uniquely powerful tool for probing the most elusive territories, the faint outskirts of massive galaxy clusters and the tenuous threads of the cosmic web that connect them. It is through this technique that we are beginning to trace the full extent of the universe's hidden anatomy, finding the warm-hot gas that theory insists must make up the final chapters of the missing matter story. Each faint distortion on the CMB map is a whisper from that ghostly ocean, a confirmation that we are finally learning to see the universe not just by the light it gives off, but by the subtle ways it bends the light that passes through. These digital universes are not mere animations, they are intricate laboratories of cosmic possibility. To guide the hunt for the missing baryons, cosmologists have constructed entire universes inside supercomputers, vast simulations that begin with a near-uniform soup of particles moments after the Big Bang, and then fast-forward through 13.8 billion years of cosmic evolution. Names like Illustris TNG and the Millennium Run represent monumental digital experiments where trillions of particles, governed by the coded laws of gravity, hydrodynamics, and nuclear physics, dance across billions of light years of virtual space. The goal is breathtakingly ambitious: to see if our understanding of physics, when applied to the entire cosmos, can produce a universe that looks like the one we actually live in. The simulations must account for everything: the relentless pull of dark matter scaffolding, the explosive feedback from supernova and black holes, and the complex cooling and heating of ordinary gas. When researchers press start, they do not know exactly what will emerge. They watch as gravity works its slow magic, as dark matter condenses into a vast cosmic web of filaments and halos. And critically, they track the ordinary baryonic matter, the protons and neutrons, as it flows along this hidden skeleton. The result is a consistent and powerful prediction. A significant fraction, roughly 30 to 40%, of all the baryons in the universe does not end up in stars or cool gas clouds. Instead, it is shock heated to millions of degrees as it falls into the deep gravitational wells of the cosmic web, settling into a diffuse, filamentary fog, the Warm-Hot Intergalactic Medium. In these digital realms, the missing matter is not missing at all. It is mapped in exquisite detail, tracing the delicate threads between galaxy clusters like a luminous spiderweb. This virtual roadmap is then compared, point by point, with our real observational data, the quasar absorption lines, the stacked X-ray hints, the subtle distortions in the cosmic microwave background. When the digital universe and the real one begin to align, it is a profound moment of validation. It tells us our physics is on the right track, and more practically, it gives our telescopes a specific place to look. The simulations act as a cosmic treasure map, predicting not just that the WHIM exists, but precisely what its temperature, density, and distribution should be in different regions of space. They guide astronomers to the most promising filaments, the areas where the signal should be strongest, turning a blind search into a targeted investigation. We are no longer groping in the dark. We are using a digital model of the entire universe to shine a light on its own hidden corners. Galaxies are not static islands, but dynamic engines with a powerful exhaust system. The story of the missing matter is not just about where it ended up, but how it got there in the first place. A critical piece of this cosmic journey involves galactic winds, vast outflows of gas driven by two of the most violent processes in the universe. The first is the death of massive stars. When a star many times larger than our Sun reaches the end of its life, it does not fade quietly. It explodes in a cataclysm known as a supernova, an event so energetic it can briefly outshine an entire galaxy. These explosions do more than create brilliant light shows. They blast shockwaves through the surrounding space, heating and accelerating enormous clouds of gas, propelling them out of the galaxy at speeds of thousands of kilometers per second. The second driver is even more formidable, the active supermassive black hole at the heart of many galaxies. As matter spirals into these cosmic monsters, it releases a staggering amount of energy, not just as light, but as powerful jets and radiation pressure that can push surrounding gas clear out of the galactic disk. Together, these processes act like a cosmic bellows, blowing huge quantities of baryonic matter, now enriched with heavier elements forged in stellar furnaces, out of the galaxies and into the vast intergalactic wilderness. This process has a name in astrophysics: feedback. It is a balancing act of cosmic proportions. Without it, galaxies would greedily hoard all their gas, forming stars at a frantic, unsustainable rate and growing far more massive than any we observe. Feedback regulates this growth. It prevents galaxies from becoming too bloated, and in doing so, it performs a vital service for the cosmic ecosystem. It seeds the voids. The gas expelled by these furious winds does not simply vanish. It travels for millions of light years, eventually slowing and mixing with the primordial hydrogen and helium that fills the space between galaxies. This enriches the intergalactic medium and the warm-hot intergalactic medium with the very elements necessary for rocky planets and life: carbon, oxygen, iron, and more. We can see this process in action today. Astronomers using space telescopes observe telltale signatures of these outflows in nearby galaxies, great plumes of gas being driven from their disks. By studying these local examples, we can calibrate our models and understand the mechanics of this galactic exhalation. This links the fate of a single galaxy to the grandest of cosmic mysteries. The powerful feedback from supernova and black holes is likely one of the primary delivery mechanisms that transported a significant portion of the universe's normal matter from the bright, visible realms of galaxies into the dark, diffuse reservoirs where it now hides. The missing matter is not lost. It was deliberately, violently, and beautifully scattered, connecting the life cycle of stars to the hidden architecture of the entire cosmos. The search for the missing matter is a testament to science's self-correcting nature, a willingness to question even its most cherished assumptions. While the warm-hot intergalactic medium remains the prime suspect, the sheer difficulty of pinning it down has led a number of physicists to ask a more radical question. What if the models themselves are wrong? Could our interpretation of the universe's birth certificate, the cosmic microwave background, contain a subtle error? Might our understanding of Big Bang nucleosynthesis, the process that forged the first elements, be missing a crucial piece? These are not questions asked lightly, for they challenge the very foundations of modern cosmology. Yet they are essential, for they represent the other fork in the road of this great mystery. One path leads to a triumphant observational discovery, finally seeing what we have long predicted. The other, far more profound path could lead to a fundamental revision of our cosmic story. One alternative theory suggests that some of the missing baryons did not simply heat up and hide. Instead, they may have transformed into something else entirely, decaying into exotic, nearly undetectable particles that interact with ordinary matter only through the faintest whisper of gravity. Another, equally speculative idea proposes that a vast population of tiny, ancient black holes, forged in the chaotic first instance of the Big Bang, could be scattered throughout space. These primordial black holes, if they exist in great numbers, would contain the mass of the missing baryons but would be virtually invisible, revealing themselves only by the way their gravity bends the light of distant stars. These concepts exist at the very edge of known physics, and for now, the evidence for them is far weaker than the mounting case for the Warm-Hot Intergalactic Medium. But their value is immense. They serve as a crucial reminder that our maps of the cosmos are still being drawn. The persistent ghost in the accounting, the half of the universe we cannot see, may be more than a hidden reservoir of hot gas. It could be a clue pointing toward a deeper layer of reality, a signal that our standard model of the universe, for all its successes, is still incomplete. The hunt for the missing baryons, therefore, is not merely a cosmic scavenger hunt. It is a stress test for our entire understanding of physics, and the final answer may surprise us all. Our cosmic inventory must look beyond the brilliant beacons to the faintest flickers of light. Scattered throughout the vast web, often orbiting larger galaxies like shy attendants, are countless dwarf galaxies. These are not the majestic spirals we picture, but modest collections of a few billion stars, sometimes even less. Their dim glow is easily washed out by the glare of their brighter neighbors or the diffuse light of our own atmosphere, making them the wallflowers of the cosmic census. Yet their potential significance is enormous, for if we have overlooked vast populations of these faint objects, their combined mass could tip the scales in our search for missing baryons. The challenge is not just their modest size, but their ghostly nature. Astronomers have begun discovering a particularly elusive class called Ultra-Diffuse galaxies. Imagine a galaxy the size of our Milky Way, but with only 1% of its stars. Those stars are not concentrated in a bright core, but spread thinly across an enormous volume, resulting in a surface brightness so low it nearly blends into the blackness of space. Finding one is like trying to see a wisp of cloud on a moonlit night, a task that pushes our telescopes to their absolute limits. It raises a compelling question: if we have missed such obvious ghosts, how many more are hiding in plain sight? And what portion of the universe's ordinary matter might be quietly tied up in their faint stellar halos? This is where the next generation of astronomy enters the story. Projects like the Legacy Survey of Space and Time, soon to begin at the Vera C. Rubin Observatory in Chile, are built for this exact purpose. With a mirror over 8 meters wide and a camera the size of a small car, this observatory will not just look at the sky, it will scan the entire visible southern hemisphere again and again for a decade. It is designed to detect the incredibly subtle, to see the faint and the diffuse that previous surveys simply could not. By comparing these repeated scans, it will map the most delicate structures in the universe, potentially revealing millions of previously unseen dwarf and ultra-diffuse galaxies. While any single one is a lightweight in cosmic terms, their collective mass could be substantial. Finding them would not only add fascinating new entries to the galactic catalogue, but would also help us complete the ledger, moving a fraction of the missing baryons from the unaccounted-for column into the found category. This relentless push to see the unseen, to find the universe's faintest signatures, is how we slowly close the gap between prediction and observation, one ghostly galaxy at a time. The ultimate resolution of this cosmic mystery lies not just in our theories, but in our tools. To finally see the ghost, we must build new eyes. The next decade promises a revolution in our observational power, with a suite of next-generation observatories designed to probe the universe's darkest secrets. Leading the charge in the hunt for the Warm-Hot Intergalactic Medium is the Athena mission, a flagship X-ray observatory being developed by the European Space Agency for launch in the 2030s. Its design is a direct response to our current limitations. Athena will carry the most sensitive X-ray instruments ever built, with a colossal mirror designed to gather these faint, high-energy whispers like never before. More importantly, it will possess an extraordinary spectral resolution, meaning it can spread the X-ray light into an exquisitely detailed rainbow, capable of discerning the faintest absorption lines from ionized oxygen and other elements in the WHIM. With Athena, astronomers will not just hope to catch a glimpse. They aim to map the invisible web directly, tracing the million-degree filaments that connect galaxy clusters and measuring their density and temperature with precision. It represents our best hope for turning the subtle statistical hints we have today into a clear, detailed portrait of the missing matter's primary hiding place. On the ground, an entirely different kind of giant is rising. In the high deserts of Chile, the extremely large telescope, or ELT, is under construction. With a primary mirror spanning an astonishing 39 meters, it will collect more light than all of the world's current large optical telescopes combined. While it will capture stunning images, its most profound contribution to this mystery may come from its spectrographs. These instruments will be able to dissect the light from the faintest, most distant quasars with unprecedented clarity, allowing scientists to study the intergalactic medium in finer detail than ever before. They will probe the cooler components of the cosmic web and help us understand the full ecosystem of gas, from the warm to the searing hot, providing a complete picture of how baryons cycle between galaxies and the voids. Simultaneously, the next generation of radio telescopes and cosmic microwave background experiments will push the sunyaev-zeldovich effect technique to new heights. Arrays of antennas with vastly improved sensitivity will scan the sky, creating ever more detailed maps of the subtle distortions in the primordial light. These maps will act as a mass census for hot gas, pinpointing the diffuse plasma in the outskirts of clusters and the faintest tendrils of the web, independent of its own glow. Together, these future instruments, spanning the electromagnetic spectrum from radio waves to X-rays, form a coordinated campaign. They represent humanity's collective effort to balance the universe's oldest ledger. We are building the keys to the final vault, transforming this era of tantalizing clues and frustrating gaps into a new age of definitive discovery, where we can finally account for every atom promised by the dawn of time. This missing half of the universe is the very material from which galaxies are born. Our current story of cosmic structure tells us that galaxies do not form in isolation. They are thought to condense from rivers of cooling gas that flow along the invisible filaments of the cosmic web, gathering within the gravitational wells of dark matter halos. It is a beautiful hierarchical process where small structures merge to build larger ones over billions of years. But this story has a crucial plot hole. If half of the fuel for this process, the ordinary baryonic gas, is not in those cool, dense streams but is instead suspended in a million-degree fog, then our entire understanding of galactic growth needs a rewrite. The temperature and physical state of matter determine everything. Cool gas can collapse under its own gravity, fragment, and ignite into stars. Hot gas, however, resists collapse. It has too much energy, too much pressure to simply settle down and form stellar nurseries. So if a vast portion of the universe's raw material is perpetually hot, spread thinly across the voids, it changes the fundamental efficiency of galaxy formation. Galaxies would not be able to gather fuel as quickly or as easily as our simpler models once assumed. This means the majestic spirals and giant ellipticals we see today may have had a much more difficult stop-start journey to maturity, fighting to pull material from a resistant, searing environment. The feedback processes we discussed earlier, the supernova winds and black hole jets, are not just expelling gas, they are actively fighting against this hot halo, preventing the galaxy from reclaiming its own expelled material too quickly. It creates a dynamic balance, a cosmic thermostat that regulates a galaxy's growth. Finding the precise amount, distribution, and temperature of these missing baryons is therefore not a side quest. It is the key to calibrating the entire narrative of cosmic evolution. It will tell us why some galaxies became brilliant behemoths and others remained faint dwarfs, why star formation rates rise and fall across cosmic time, and ultimately, how a galaxy like our Milky Way managed to assemble itself from this hot, chaotic backdrop. The fate of the missing matter is inextricably linked to our own galactic story, a hidden chapter that explains the conditions that made our cosmic home possible. The universe's budget is a ledger with 3 dominant entries, and we have only just begun to read one of them correctly. While the hunt for missing baryons is a distinct mystery from the profound enigmas of dark matter and dark energy, its resolution is not an isolated event. Think of our cosmic understanding as a 3-legged stool. One leg is dark matter, the invisible gravitational glue that holds galaxies and clusters together. The second leg is dark energy, the mysterious force accelerating the expansion of the cosmos. The third leg is baryonic matter, the ordinary atoms that build everything we can touch and see, from stars to planets to ourselves. For the stool to stand firm, we must know the precise length and strength of each leg. If we are wrong about the amount of normal matter, if our accounting is off by trillions of suns, then our measurements of the other 2, more mysterious components become shaky and uncertain. Dark matter is detected indirectly through its gravitational pull, by watching how it bends light or dictates the rotation speeds of galaxies. But to calculate exactly how much dark matter is present in a galaxy cluster, for example, we must first subtract the gravitational contribution of all the normal matter within it, the hot gas, the stars, and the galaxies. If we have underestimated the amount of that normal matter hiding in a hot, diffuse halo around those galaxies, then we have also overestimated the amount of dark matter needed to explain the cluster's total gravity. Solving the missing baryon puzzle is therefore an act of cosmic bookkeeping that sharpens our view of the dark universe. It refines the numbers in our most fundamental equations, allowing us to pin down the properties of dark matter and dark energy with far greater precision. It ensures that our models of cosmic evolution, from the first microseconds after the Big Bang to the universe's distant, fading future, are built on a foundation of accounted-for reality, not on hidden errors. By finding the half of the ordinary world we have lost, we gain a clearer lens through which to finally perceive the profound darkness that surrounds it. This search for the missing half of the cosmos does more than fill a ledger, it reshapes our very sense of reality. For centuries, we have looked to the night sky and believed that what we see is what exists, a tapestry of stars and darkness. This detective story reveals a far more profound truth, that our perception is a narrow window, a limited view of a universe teeming with hidden realms. The brilliant galaxies and nebulae we photograph are just the luminous ornaments hanging on a scaffolding we cannot see, suspended in an ocean of matter we are only now learning to sense. It is a humbling reminder that the universe is under no obligation to be obvious to us. the vast majority of its structure and substance operates in a register of energy and scale that our biological senses and even our early instruments were never designed to perceive. We have built our understanding of reality from the tiny sliver of light that happens to be visible to our eyes, only to discover it is like trying to understand a vast, complex city by only ever seeing the neon signs. The real substance, the infrastructure, the power lines, and the plumbing has been invisible all along. This realization echoes through human culture and philosophy. For ages, stories and myths have spoken of unseen worlds, of spirits in the air or realms just beyond sight. While this scientific discovery is grounded in physics, not mythology, it touches a similar nerve, a deep-seated intuition that there is more to existence than meets the eye. The warm-hot intergalactic medium and the dark matter web are not supernatural, but they are supernatural forces and structures that operate on a scale and in a state that fundamentally transcends our everyday experience. They are hidden realms as real as the ground beneath our feet, yet requiring immense ingenuity and patience to reveal. This transforms our cosmic narrative from a simple story of stars and planets into an epic of layered realities, where most of the action occurs in a theater we are only beginning to enter. It challenges a very human-centric view of the universe, reminding us that we are not the center, nor are we even privy to the full stage. Our home is a small, bright corner of a vast architecture that is mostly dark, mostly hot, and mostly silent to our conventional ways of looking. This is not a cause for despair, but a source of endless wonder and inspiration. It means the universe is far stranger, more intricate, and more mysterious than it appears on a clear, starry night. Every time we answer a fundamental question, like where the missing matter has gone, we do not close a book, we open a door to a hallway with many more doors. The search itself becomes a testament to human curiosity, a drive to push beyond the limits of our senses and comprehend the full, hidden majesty of our cosmic home. It demonstrates that the greatest discoveries often lie not in finding new landscapes, but in gaining new eyes, in learning to see the profound and beautiful reality that has been there all along. This grand cosmic search is not confined to the silent halls of research institutions. The hunt for the missing half of the universe is, at its heart, a profoundly human story, one that invites all of us to participate. While the intricate data analysis requires the expertise of professional astronomers, the narrative of the mystery itself is a gateway. It transforms complex astrophysics into a relatable detective story, a puzzle on the grandest possible scale. This accessibility is a powerful tool for public engagement, turning distant science into shared wonder. We have already seen the incredible potential of this collaboration in projects like Galaxies. For years, this online platform has invited people from all walks of life to look at telescope images and help classify galaxies, a task where the human eye for pattern can still outperform even the most sophisticated algorithms. Volunteers have discovered rare and unusual galactic structures, contributing directly to published scientific research. This model of citizen science offers a compelling blueprint for the next phase of our search. As observatories like the Vera C. Rubin Observatory come online, they will not just collect data, they will generate a flood of it, an ocean of images containing billions of celestial objects. Hidden within that ocean could be the faint, ghostly signatures of the missing matter's influence, or countless new ultra-diffuse galaxies that have slipped past previous surveys. The task of sifting through this unprecedented volume of information is monumental. Here, an engaged global community could become an invaluable partner, helping to spot the subtle, the strange, and the diffuse that computers might initially overlook. By sharing this cosmic mystery widely, we do more than just recruit helpers, we foster a vital connection. It builds a bridge between the cutting edge of human knowledge and the innate curiosity that leads anyone to gaze at the night sky. It reminds us that this is not a remote academic exercise but a shared exploration of our home. Every person who learns about the missing baryons and looks up with a new question is participating in the story. This engagement inspires the next generation of scientists, engineers, and dreamers, ensuring that the long, patient work of mapping the hidden cosmos continues. It is a reminder that the universe's greatest secrets are not for a select few to uncover, but a collective human endeavor, inviting all of us to look up and wonder about the invisible architecture holding everything together. Our own galactic backyard offers a crucial testing ground for this cosmic hunt. Within a sphere a few 100 million light-years across, a region cosmologists call the local universe, we have an unparalleled advantage. Here, our maps are incredibly detailed. Projects like the Sloan Digital Sky Survey have painstakingly catalogued the positions of millions of galaxies, allowing us to chart the large-scale structure with remarkable precision. We can see where the great walls of galaxies lie, and more importantly, we can predict where the invisible filaments of the cosmic web, the supposed highways of the Warm-Hot Intergalactic Medium, should connect them. It is like having a detailed blueprint of a city's road network. With this map in hand, astronomers can point our most powerful X-ray telescopes, like XMM Newton and Chandra, at the empty spaces between the bright galactic landmarks, directly targeting the predicted locations of these hidden filaments. The goal is not to see a glowing thread, but to detect the faintest whisper of X-ray emission or the subtle absorption signature in the light of a background source, proof that the predicted highway is indeed filled with traffic, albeit traffic made of million-degree plasma. Several ambitious observing campaigns have done exactly this, focusing on the spaces between massive structures like the Sculptor Wall or the filaments extending from our own local group of galaxies. The results are tantalizing but require the most careful interpretation. Detections are often reported as slight excesses of soft X-ray glow in a specific direction, or as a handful of absorption lines from highly ionized oxygen in the spectrum of a distant quasar, lines that align perfectly with the predicted path of a filament. These signals are not blazingly obvious. They exist at the very edge of what our current instruments can reliably measure, often requiring hundreds of hours of observation time to gather enough photons for a statistically significant result. This local search functions as a controlled cosmic experiment. The distances are manageable, our maps are accurate, and we can repeatedly observe the same patch of sky to confirm or refute a signal. A definitive, reproducible detection in our local universe would achieve two monumental things. First, it would directly recover a measurable portion of the missing baryons, proving they are indeed woven into the web as predicted. Second, and perhaps more importantly, it would validate the entire forensic toolkit. It would show that our methods of stacking data, hunting for absorption lines, and interpreting subtle X-ray excesses are correct. Success here builds the confidence needed to scale up, to apply these same techniques to the deeper, more ancient universe where the signals are even fainter and the maps less distinct. It turns a theoretical prediction into an observational protocol, moving the mystery of the missing half from a question of if it exists to a question of exactly how much and where. Solving the universe's greatest puzzles requires tools that do not yet exist. This relentless drive to see the unseen, to detect the faintest whisper from a million-degree filament, has become a powerful engine for technological innovation. The specialized instruments built for this cosmic hunt often find a second life, transforming fields far removed from astronomy. Take the development of ultra-sensitive X-ray detectors, designed to catch the ghostly glow of the warm-hot intergalactic medium. To achieve this, engineers must push the boundaries of material science, creating sensors that can register individual photons with incredible precision while operating in the harsh environment of space. These advancements do not stay locked in a telescope. They directly influence the next generation of medical imaging devices. The same technology that maps hot gas in a distant galaxy cluster can be refined to create more detailed and less invasive X-ray scanners for hospitals, improving early diagnosis and treatment planning. It is a direct transfer from the cosmic scale to the human scale, where the quest to understand the universe's structure helps us better see the intricate structures within our own bodies. Similarly, the advanced spectrographs created to dissect the light from quasars demand extraordinary optical precision and stability. The techniques developed to manufacture the flawless mirrors and diffraction gratings for these instruments often lead to breakthroughs in laser technology, telecommunications, and even the fabrication of advanced semiconductors. The algorithms written to sift through the cosmic noise, to find the faint signal of a hidden filament buried in terabytes of X-ray data, are masterclasses in pattern recognition and statistical analysis. These sophisticated codes are increasingly adapted for use in climate modeling, financial forecasting, and artificial intelligence, helping us find patterns in complex systems here on Earth. The challenge of the cosmos forces computer scientists to develop new ways of thinking about data, solutions that then ripple out into countless other disciplines. Perhaps the most profound spin-off lies in the realm of pure computation. Running a simulation like Illustris TNG, which follows trillions of particles over billions of years, is one of the most demanding tasks ever conceived. It stretches the limits of supercomputer architecture, requiring innovations in parallel processing, data storage, and energy efficiency. The software frameworks created to manage these digital universes become testbeds for solving immense, multi-scale problems. The lessons learned are now applied to simulating molecular interactions for drug discovery, modeling global weather patterns with greater accuracy, and optimizing vast logistics networks. The cosmic laboratory, in its need to simulate everything, ends up advancing the very art of simulation itself. This demonstrates a beautiful and often overlooked truth about fundamental research. The pursuit of a deep, curiosity-driven question, like the location of the missing half of the universe, rarely yields a single, isolated answer. Instead, it builds a towering ladder of new capabilities, new materials, and new methods. Each rung on that ladder supports not only astronomers peering into the void, but also engineers, doctors, and entrepreneurs building a better future here on the ground. The search, therefore, is more than an accounting of cosmic material. It is an investment in human ingenuity, proving that when we aim our collective curiosity at the farthest horizons, the tools we forge along the way illuminate our path in unexpected and profoundly practical ways. The pursuit of such profound mysteries comes with a profound responsibility. A telescope like Athena or an observatory like the ILT represents an investment of billions of dollars and decades of human effort, resources drawn from a world with urgent needs here on Earth. It is a valid and necessary question to ask. Why should we spend so much to find invisible gas in the distant voids when there are challenges of health, environment, and well-being that demand our attention and funding? The answer is not found in dismissing one need over the other, but in understanding the unique role of fundamental science. This kind of research is not a luxury or a diversion. It is the deepest form of human exploration, a reach for context. By striving to understand the universe's most basic rules and its complete history, we are essentially asking the biggest questions about our own existence. Where did everything come from? What is it all made of? How does it all fit together? The value lies not in the immediate application of finding a hot filament, but in the act of looking itself. Historically, this pure pursuit of understanding has a remarkable track record of yielding unexpected, transformative benefits. The entire technology of the global positioning system, for instance, is built upon Einstein's theory of relativity, a framework developed from a scientist's curiosity about the nature of space and time, not a plan to build better navigation. The World Wide Web was invented at a particle physics laboratory to help scientists share data. The sensitive X-ray detectors we build for cosmology advance medical imaging. The question is not whether we can afford to explore the cosmos, but whether we can afford to stop asking the questions that have always pushed our species forward. Furthermore, these monumental projects are almost never the work of a single nation. They are triumphs of international collaboration, requiring the shared expertise, funding, and goodwill of dozens of countries. In a time of global divisions, the coordinated effort to build a space telescope or operate a giant observatory stands as a powerful counter-narrative. It demonstrates that humanity can still unite across borders, driven not by conflict, but by a shared, peaceful curiosity. Scientists, engineers, and students from around the world work toward a common goal that belongs to no one country, but to everyone under the same sky. This cooperative endeavor to map the cosmic web becomes, in itself, a web connecting human minds across the planet, reminding us that our desire to comprehend the universe is a trait we all share, and perhaps the most hopeful project of all. The scattered clues from across the cosmos are finally aligning into a single, breathtaking portrait. From the ancient deuterium in pristine gas clouds to the subtle ripples in the first light, from the dark lines in quasar rainbows to the faint X-ray glow of stacked filaments, every independent line of inquiry points toward the same hidden reality. The universe's missing atoms are not absent. They form a colossal, diffuse ocean, a superheated plasma woven through the vast architecture of space itself. This warm-hot intergalactic medium traces the invisible scaffolding predicted by dark matter, clinging to the filaments that connect galaxy clusters in a shimmering, million-degree web. It also pools in immense halos around galaxies like our own, vast coronas of searing gas that represent a galaxy's true, extended form. While the final accounting is not yet complete, and some baryons may still lurk in even more elusive forms, the convergence is undeniable. Multiple detective techniques, each with its own strengths and weaknesses, are all sketching the same ghostly shape in the darkness. This is how science builds certainty, not from a single eureka moment, but from the slow, patient accumulation of evidence that all whispers the same answer. The puzzle of the missing half is transforming from a crisis of confidence into a triumph of methodology. We are learning to see with new eyes, to perceive a universe where the bright, shining galaxies are merely the glittering ornaments on a hidden, luminous tapestry that has been there all along. The mystery of the missing half of the universe stands as a towering testament to the relentless and ingenious spirit of scientific inquiry. It is a decades-long quest, a cosmic accounting project to trace the fate of every single atom born in the Big Bang's fiery dawn. We began with a simple, startling discrepancy, a primordial receipt from the universe's first moments that promised far more ordinary matter than our telescopes could ever find. From that initial puzzle, we followed a trail of clues etched into the light of ancient quasars, hidden within the subtle distortions of the first light, and whispered in the faintest X-ray glow from the spaces between everything. This journey has forced us to look beyond the brilliant galaxies and stars, to develop new eyes that can perceive the universe's hidden anatomy, a vast, searing web of plasma that connects all structures in a luminous, million-degree embrace. While the final, precise accounting of every baryon awaits the next generation of telescopes, the path of discovery has already irrevocably changed our cosmic perspective. We no longer see a universe of isolated islands of light floating in an empty black sea. We now understand it as a continuous, dynamic structure, where the bright galaxies are merely the densest knots in a grand, intricate tapestry, most of which glows in a light we are only just learning to see. This story is far more than a solved puzzle. It is a powerful reminder of how science operates, not through sudden revelation, but through patient, collaborative detective work that slowly pulls back the veil on reality. The cosmos remains full of secrets waiting to be uncovered, from the nature of dark matter to the destiny of dark energy. Each answer we find simply reveals deeper, more fascinating questions. So keep looking up, nurture that sense of wonder, and let us know in the comments what part of this great cosmic detective story captivated you the most.